So here are a couple problems from a calculus textbook, and they ask us to find all the discontinuities of f of x, and then if we know we have a removable discontinuity, to define a new function so that it is removed. So in number 17 here, what we have is we have a product of x squared. X squared is always continuous, polynomials are always continuous, so we don't really have to worry about this a whole lot, times tangent of x. Now, tangent of x is not continuous. So what we're going to have to do in order to figure out where the product of these two functions is discontinuous is we're going to have to figure out where tangent of x is discontinuous. And you should hopefully recognize that tangent of x can be rewritten as sine of x over cosine of x. And this fraction is definitely going to have a denominator of 0 anytime cosine of x equals 0. So what we're going to have to do here in order to figure out what the discontinuities of f of x are is set cosine of x equal to 0 and then attempt to solve that. So if we go to the unit circle, we should be able to use it to allow us to see when cosine of x equals 0. So any point on the unit circle is going to have coordinates x comma y given by cosine of theta comma sine of theta. We want to know where cosine is equal to 0, so essentially we want to know where on the unit circle we have locations where the x coordinate is 0. So at this angle right here, measured from the positive x-axis, you'd probably recognize that that's going to be the angle pi by 2, and this would be pi. This angle down here would be measuring 3 pi by 2. So the unit circle shows us two values in between 0 and 2 pi where this is true. This is kind of a weird situation because in this problem we actually have an infinite number of discontinuities. There are an infinite number of places where cosine of x equals 0. It happens at pi by 2. It happens at 3 pi by 2. This is 2 pi. This is, if we continue to go around and around and around the unit circle, 2 pi, pi by 2 past that would be 5 pi by 2, 7 pi by 2, 9 pi by 2, 11 pi by 2. So the places where our function is discontinuous, or the places where cosine of x equals 0, would actually be an infinite number of them. We have pi by 2 as the first one we noticed, 3 pi by 2 as the next one, 5 pi by 2 as the next one, 7 pi by 2, 9 pi by 2. I'm just going to do, all right, we've started a pattern, dot, 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 pattern continues. The other thing about the unit circle that we don't talk a ton about with regard to the unit circle, usually we're between 0 and 2 pi on the unit circle, but we can actually go in reverse. If we start at 0 and open downward from the x-axis, that's going to measure negative pi by 2, negative 3 pi by 2, negative 5 pi by 2, so we're going the opposite direction around the unit circle here. So I'm just going to show that this pattern also goes back this way. So this function has an infinite number of discontinuities. You know the graph of tangent of x, if you've seen it before, has a bunch of vertical asymptotes. Since this function, one of the pieces of the product is tangent of x, this function is also going to have a bunch of vertical asymptotes, and they're going to happen at these x's. So we are discontinuous at each of these x's because the function is undefined at each of those x's. Now if we look at number 19 here, we have, again, a product of two functions. Individually, x is just a line, and that's continuous. But natural log of something is not necessarily always going to be defined. So the piece of this one we have to worry about is, again, the second component of it. So we're going to have to be really careful with this natural log of x squared portion. We want to know when this is undefined. Now, we've looked at the graph of natural log of x off and on all year. I am not graphing this right now. I'm graphing the natural log of x. So the graph of y equals the natural log of x looks something like this. Why am I looking at this graph right now? Well, I want to use it to allow myself to realize what numbers I'm allowed to have inside this natural log function. We don't have a point on this graph at the x of 0 or at any x's that are negative, right? No graph over here to the left of the y-axis, no place on this graph where we cross the y-axis. So no place where x equals 0, no place where x is negative. That's what the graph of natural log of x tells us. Natural log of something, the something can only be a positive value. So we would need to know when x squared is greater than 0. And if you think about when x squared is greater than 0, you're hopefully going to realize that if you put a negative in place of x and square it, it's positive. And a positive squared is also obviously positive. But this inequality is not going to be true when x equals 0. I can't put 0 in place of x, square it, and then take the natural log of the result. The natural log of 0 is undefined. Now the weird thing that happens here is that the negatives are allowable, and that's really only because of the exponent on the x. So the domain of this function is actually going to be from negative infinity to 0. We can't include 0. We can include all these negatives because we're squaring them inside the natural log and they become positives. And then from 0 onward to infinity. The only place where this product is going to be undefined is going to be at the x value of 0. So our function is going to be discontinuous at x equals 0. So the thing that you have to do when you're trying to find discontinuities is generally going to be to figure out where your function's undefined. I looked at these two examples because they're a little different. We didn't have to worry about the whole entire function. We didn't necessarily have denominators here initially. So we had to take a slightly different approach than what you would in a rational function to determine where it's undefined. But this is the approach that you'd want to take. The only other situation that you might run into where you're going to have a discontinuity would be a piecewise function. With a piecewise function, you have to worry about jumps happening at the x values where you transition from one piece of the function to the next.